Hello and welcome to the CIBSE West Midlands region CPD webinar on district energy, guaranteeing performance and where it is heading, provided by Neil Parry at Armstrong. Just a few housekeeping tasks before we get started, if I may. Please use the chat function to ask any questions during the presentation and I'll relay them on to Neil. A copy of the presentation slides should be available after the event via our website. CPD certificates will be sent automatically afterwards once I've checked you in via your registered contact details. I'd like to take the opportunity to thank you all for joining us for today's session, but also to thank Neil for sharing with us what he's about to share. I'm really looking forward to hearing it. So, a brief description on the topics covered in the CPD. Why district energy? A look at Swedish heat networks, renewable energy integration, forecasted DHC growth, district energy, the great facilitator, where does our energy go, the hierarchy of importance, making district energy efficient, maximising delta T and lowering return temperatures, the design process, project performance examples, sizing calculations, pump staging, plant room design and plant room common issues, pre-packaged plant rooms, thermal storage, stratification, utilisation, approach temperatures, heat pump only networks, and sector coupling. Neil Parry is an engineer whose early career includes applications engineer, product manager, and technical department manager. His district heating career includes over 20 years experience in the market, including Danfoss, SAV, Caleffi and Armstrong, managing a team of sales engineers, services engineers, and the technical departments. A CIBSE accredited heat network consultant, along with a CIBSE registered lecturer, Neil currently sits on the steering group for BSRIA BG62 Heat Networks Design Guide, DPCV SG and PICV SG, and is a peer reviewer for CIBSE CP1 2015 and 2020, along with Fairheat BESA HIU tests. He's currently writing the British standard for HIU BS8635, although the number is subject to change, and is an active member of the ADE, UKDEA, Euroheat, and Power and IDEA. Neil, it's great to have you with us this evening. Thank you very much, and looking forward to your presentation.
Thanks, Josh. I'll get straight in. As Josh has outlined some of the aspects I'm going to touch on. As you've just heard, there's quite a few in there. So I've tried to cover every little aspect really, which means I don't go into too much depth or too much detail. But if you do have a question, as Josh said, please put it into the chat. My contact details will be shown at the end on the last slide. So if you have something that's much more involved, then please feel free to contact me on my email address, and we can get right into the depth of whichever aspect you want to look at. So without any further ado, I shall press on. So just having a little trouble advancing the slide. Okay, right. So I'm not going to go through the agenda. Josh has done that, and you've seen that little bit about me. The only thing I think that was missing is I'm now on the technical working group of HNTAS, the Heat Network Technical Assurance Scheme, which is run by DESNES, the government's energy department. So why district energy? Well, what I've done first of all is a very quick calculation on the left-hand side of this slide, where we're looking at 5 individual buildings with 5 individual plant rooms. If you add up all those plant rooms, you find that the calculation tells you you need 38,715 litres of thermal storage, 5,385 kilowatts of energy, and a peak flow of 88.95 litres per second. If you connect those same 5 buildings to a centralized or a decentralized energy center rather, then because of you're adding them together, you get diversification of load, and you can see from the calculations that everything is a little bit smaller. So smaller thermal store, lower amount of energy required, and a smaller peak flow rate to do the same loading. So that's really one of the benefits. I've also listed out what that equates to in terms of the text in red and green. I'm not going to read through those, but if it's red, obviously it's a negative, and if it's in green, it's a positive. So looking over at the graph on the right hand side, what you can see there is the resultant demand profile because of the aggregation of the loads. So the blue line shows you what an individual demand profile would look like, very high peaks and then times of zero demand. And as you add more and more apartments or more buildings, etc., onto the energy center, you find that the peaks and troughs tend to be to get smoothed out. You also obviously increase your base load, so you've got something for your renewable energy sources to go at, if you like, before you get to the peaking area, where a lot of that peak can, of course, be supplied from thermal storage that you're using your renewable energy to load prior to those peaks. So what you tend to find is your peaking energy sources tend to be more carbon intensive, and by amalgamating those loads, smoothing those peaks and troughs, you can reduce the requirement for that fast modulating energy source. And finally, if you add instantaneous hot water generation into the mix, then typically you tend to reduce your return temperature by, on average, something around 8 to 10 degrees C. And what we'll see a little bit later on is the advantages that come out of having a greater delta T or a lower return temperature. Those two phrases are pretty much interchangeable, but we'll look at that in a much more detail as we move on. So there are lots of bits of data and graphs and pie charts and you name it that show you the benefits of district energy, but I tend to stick with these two graphs here because I think it shows it very, very well. The graph on the left-hand side shows you the amount of heat supplied in petajoules per year into district or into buildings via district heating systems in Sweden from the years 1969 up to 2015. And what you can see there is a significant and constant, really, increase in the amount of energy supplied via district heating. When you compare that to the graph on the right-hand side, which is showing you the applicable emissions associated to that energy supply, you can see that they've dramatically reduced. And it's something I tend to talk a lot about. You know, everyone's or most countries have signed up to being net zero at some point, and if we're going to achieve it, we need to make wholesale change. You know, we're not going to get there by expecting every individual house owner, apartment owner to make a change that reduces the carbon emissions. We need to do it wholesale if we're going to get there in time, and that's what heat networks do. It's a proven method of significant and large reduction in carbon emissions and the integration of renewable energy. So I've just mentioned renewable energy as well. What have I got here to sort of convince you to that? Well, what we're seeing here in this graph is basically the amount of energy supplied into for heating and cooling. This is not just looking at district energy at the moment. So the amount of energy supplied into buildings for heating and cooling and the share of renewable energy in that supply of heating and cooling. And what you can see is, as you would expect, some countries have less renewable energy integration, some have more. But what is very telling is that the top 6 countries, in terms of the greater share of renewable energy in their heating and cooling supply, are also the top 6 countries in terms of the share of district energy that in the supply. So the greater the uptake of district energy, the more renewable energy, and the two go hand in hand. So they are intrinsically linked. So if we want to increase the renewable energy use, then we need to increase the amount of district energy that we provide that energy by. So looking at the forecasted growth, pretty much every country is forecasting a growth in district heating or district energy. It varies between countries, and when you start to dig down deep into the data, sometimes you see very detailed information on how they're going to do it and how much it's going to increase, and you're looking point something percent. But then there are some other countries where you look at it and it seems to be very quickly put together, where you get figures like, oh, we're going to do 10, and then we're going to do 20%, then we're going to do 30%, very rounded up. So some of the data is a little bit difficult to get hold of, but it doesn't really matter which country's data you look at. Pretty much every country is predicting significant increase in the amount of energy supplied via district heating. Looking at the UK, currently we're around about 3% of energy. So that what that basically means is 3% of energy supplied into buildings comes from district energy. So a really very low figure. The prediction is that will be increased to 5% by 2030, 12% by 2040, and then 19% by 2050. In my opinion, that's still a very lowly figure, and we need to work very hard at increasing that. When you look at the graph, you can see some great examples there. Denmark, Finland, Sweden, with very high district energy use. Obviously, the more buildings you have on district energy, the harder it gets then to increase further, because you start to have to deal with the really spread out areas, which can be difficult to get onto district energy. But on that subject, although you can see the figures there for Denmark, they've actually now recounted those figures, and they're pushing to a greater extent, and they're hoping to top 80% by 2050. So pushing harder into the district energy arena, because they've had so much experience of it and they know that it works, and that's simply what's happening there. So when I refer to district energy, very often I refer to it as the facilitator, because district energy is completely energy source agnostic. You can use any variety of energy source and combinations of energy sources, and it really does facilitate the use of those sources, but also waste energy as well. So I often get asked about things, what's the next the next big thing in district energy, and people are normally looking for some kind of energy source as a silver bullet. And I've been in the game long enough to have seen sort of solar being touted as this is the next big thing, this is what's going to dominate, and then we had CHP, that was the next thing, that was the silver bullet, and then latterly, of course, heat pumps. And I firmly believe that there's no such thing as a silver bullet in terms of energy sources, but what there is, in my view, the nearest thing you're going to get to a silver bullet is actually the district energy network itself, because it is that network that allows that integration of various different sources and waste energy, as I mentioned. It also allows for step changes in the reduction of carbon, so wholesale reductions, because if you can imagine a network that's currently running on gas, so has quite a high carbon implication, there could be 6,000, 10,000 homes connected to that network. When you make the change at the energy center to reduce the carbon energy sources to low carbon or zero carbon sources, what happens is the moment you switch that on, those 6,000, 10,000 people benefit from that change overnight. So it allows that step change. And what we'll see later on when we look at sector coupling is that district heating and district cooling are two of the 4 power grids that enable sector coupling. And to be blunt, sector coupling will not work without district heating and district cooling integrated within it. So it's future-proofing the supply of heating, domestic hot water, and cooling, reduces those peaks and troughs, as I mentioned, and it also, very importantly, facilitates the easy integration and utilization of thermal storage. And we'll look at that on a number of slides as we move forward. So just looking at a couple of upcoming legislation, really, all with the intention of speeding up our uptake of district energy in the UK, and moving us from that current 3% that I mentioned up to the 19-20% by 2050. The first one is heat network zoning. This is where certain areas within the country are designated as a heat network zone. And in those areas, the connection of buildings to that heat network zone that heat network system rather will be encouraged. That, you know, if you're building here, if it's new build, you need to connect to this district energy network. If it's an existing building, then again, you'll be encouraged to connect, I think is the phrase that's being used. So it's really accelerating that. And there is a trial underway currently in having various zones and seeing what effect that has on the buildings that go on in that particular area. And then the other thing you have, as I mentioned earlier on, is the Heat Network Technical Assurance Scheme, something I'm involved in. This is really aimed at improving the efficiency and the performance of heat networks. And unfortunately, I have to say, we've not been very good in this country in getting efficient district energy systems. We tend to operate them on very low delta Ts, which is not efficient at all. Lots of other things that we tend not to do very well. So the intention here with this technical assurance scheme is really to follow along and develop from CP1 and improve on the technical aspects of the build, be that the energy centre, the district pipework, the substations, if there are some in the individual buildings, then the distribution network, the consumer connection, and the consumer heat system itself. So all areas really of a heat network. And it is a toll gate process, which basically means that as you progress through the build, that you will get to points where the system as it stands has to be verified that it meets the requirements of the assurance scheme, and only then, when that's been assessed and approved, can you then move on to the next stage in that design. So it's really very restrictive from that point of view, but it is efficiency and performance based, and it's really crucial. And I think it's a great move, having been involved in or seeing poorly performing systems and trying to optimize them, and first of all work out what's going wrong, where the issues are. This should be a way of assuring that systems like that are reduced to the bare minimum. So we're not going to spend a great deal of time on this particular slide. It's just showing you really where our energy goes in the building sector, basically. And you can see there's a huge chunk of that is in the residential space heating area. So there is something called the hierarchy of importance. It's just really where you need to focus your time and energies really in the first instance and work through this process. Now, it's been mentioned very often, or in a number of circles I've been in, that the cheapest energy is the energy that you don't use. So that's the first place to start. Let's just use less energy. Now, that is intrinsically linked with the second aspect, which is to reduce energy waste. So, you know, look at maybe insulating the building to a greater extent, making it more airtight, maybe having flow restrictors on taps, etc., to reduce energy use and reduce energy waste. Then move on to utilizing waste heat sources wherever possible, because obviously that energy is already there. It makes sense to use it. Then utilize any renewable energy sources you possibly can, and finally, if you get down to an area where you have no choice and there is some carbon involved in the energy sources, then look to offset that. Always makes me a little bit nervous, that statement, because I think it, unless it's managed correctly, then you have the potential for some issues arising there, where we can just go, oh, we'll just offset things and it's all fine, and that's certainly not what the intention should be at all. So you can see how you work through those factors, and I've just put a little thing there saying don't end, because you know it's right to continuously keep looking at what's going on in the building, and can we optimize, can we address some of these other aspects again, maybe revisit them and improve further wherever possible. So it's an ongoing and continuous process. So if you're a mechanical engineer, you've probably got that formula that you can see there tattooed on the inside of your eyelids. It basically shows you that the flow rate required equals the power required divided by your thermal transfer constant, 4.2, I've rounded it up slightly, multiplied by the delta T. So in terms of the kilowatts, as I mentioned earlier, we can look at that. We can address that in some way by that extra insulation, as an example, and reducing flow rates of taps, etc., etc. But at some point, you're going to come to the point where you've minimized the energy use as much as possible, and you have a figure that is the kilowatts you actually need for that building. Obviously, we can't affect the transfer constant, but what we can do is affect that delta T. And the bigger we make that delta T, the smaller the flow rate is that's required to give you that amount of power that you need. So we really need to focus on that delta T. And if we can maximize that, normally by reducing the return temperature, then lots of things cascade down from that. We reduce heat losses from the network because you've effectively got one hot pipe and one much cooler pipe, so you've reduced those losses. We reduce the flow rate that's required, so your pump energy is less, the size of your pump is less. You've reduced system inertia, and this is a very interesting aspect of district energy or district heating systems and district cooling systems, in that the greater the size of the pipe, the bigger the inertia, or the greater the inertia in the system. And that means then that you kind of lead yourself down a path where you have to keep a lot of circulation going around that system, because you don't want that water to cool, because if you do, there's so much volume in that system that you have to purge through your terminal units before you can actually get the output that you need. So by lowering the required flow rate, we reduce the pipe sizes, we reduce the volume on the primary system, and we speed up response times for anything, whether it's cooling or for heating or for domestic hot water. It becomes more critical, of course, when we look at domestic hot water response times. But it's one of the key aspects that we need to focus on. And of course, the lower that return, the more your condensing boiler will condense. It's not a threshold that we need to just get over and then relax. We've done it. The more we can get that to condense, the more efficient it will be. And when we start to look at some renewable sources, let's just say solar and heat pumps here, we tend to see a flow temperature, around about 50, 55 degrees. If what our return temperature is 50, 55 degrees, then we can't actually add anything from that renewable energy source. Now, when we look at CHP, obviously CHP is capable of higher output temperatures, but of course, if we have a high return temperature going back to the CHP engine itself can't get rid of its heat, and then it will have to switch off, and you lose your electricity output as well as your thermal output. When you look at things like thermal store sizes, plant room pumps, and then all the pipe work, and of course, therefore fittings and valves and so on, reducing that required flow rate reduces the size of all those. And for all those items, there's obviously a capex and an opex saving, because it's obviously less costly to use smaller equipment, and in operation they're using less energy or emitting less energy. So there's a double whammy there where you're gaining twice. So how do we then make district energy efficient? Well, hopefully I've convinced you it's about maximizing the delta T, or reducing the return temperature back to the network. We need to also look at bypasses, and it's a key area. CP1 itself says, we need to reduce the number of bypasses on the system. We have to remember, of course, that a keep warm or a standby flow rate through a HIU or terminal unit is a bypass, of course. So we need to think about that. We need to be very careful about selection of equipment to make sure that we reduce that bypass flow rate wherever possible. Select equipment that manages that bypass very, very well. But also, if we calculate that we need to have some system bypasses somewhere on that system, that's okay to do that, but we need to make sure that we valve it correctly and commission that valve correctly, so that flow rate through that bypass is kept to an absolute minimum. We need to look from the pump's point of view about how we maximize that pump turn down. We need a really big delta between peak demand and low demand. Maximize that as much as possible. And today's pumps, we can typically get down to 5 to 8% of peak load without any too many issues at all. Accurate plant room sizing, so don't oversize the energy sources. There's often a tendency to say, well, I think I don't want to cut things too tight, so I'm going to add a bit of extra in here and then add a bit of extra over there, and these things start to add up as you go through the sizing calculations, and they tend to compound each other, and we end up, you know, significantly oversizing things. Particularly bad from a pump point of view as well, because then by having a much larger pump, you find that it can't turn down far enough, and you've got a much smaller then operating delta of between the peak flow and an idle flow, if you like. Absolutely use the correct diversity in the hot water calculation. Look at using diversity in the heating calculation, something that's recommended in CP1 again. Definitely maximize the utilization of that thermal store, and ensure that you don't connect it in such a way that allows flow through the vessel, so you have circulation around the sources and through the vessel, because that will minimize the amount of energy that you have in the store and raise that return temperature back to your sources. So you need to ensure the stratification there in that store. And then once you have that, you can actually then start to control your energy sources using that stratification layer as an indicator of what's going on and an indicator of the balance between output and demand, and control accordingly. And we'll look at approach temperature a little bit later on, so I'll talk about that later. Utilize underfloor heating wherever possible. Accurate pipework sizing, and I'd suggest moving certainly on the lateral pipework away a little bit from the sort of standard 250-300 pascals per meter, and look at increasing that up to, say, 600 pascals per meter. You'll find that you'll still probably be well within the velocity limits outlined in CP1, but the objections to that normally are, well, what about erosion? What about noise? And we have to remember this is a variable volume system where the peak demand occurs for a very small period of time, and you know, it only occurs when there is high domestic hot water demand. So any noise you're not going to hear much at all, because if at all, because you're going to be running a bath typically. That's what's creating that high primary flow rate, so you're not going to hear that. And secondly, as for erosion, you know, the peak occurs for 10 to 15 minutes in a 24-hour period, so it's hardly ever occurs that high velocity. So high levels of lagging, again, I'd say use the guidance in CP1, which is pushes or promotes a thicker level of lagging than is typically in most of the standards. And then one of the key aspects with any district network is to work back from the far extremities of the system. So even in that those index apartments, you'd start to look at the radiators, the heat emitters, and make sure they're balanced properly. Make sure that pressure independent TRVs are used. Utilize gas heads because they're faster reacting, and then slowly work your way back towards the plant room. If the heat emitters in the apartments are not balanced very well or correctly, you're going to really struggle to hold a good delta T on the system. And then finally, look at lower flow temperatures. We've got to be mindful that as we lower that flow temperature, the return temperature will come up a little bit. But the benefits of lowering that flow temperature and the reduced losses on the network do actually outweigh that difference, that slight reduction in delta T. So just looking at approach temperatures, I've done a couple of calculations here, looking at terminal units that you would typically get in an apartment. These would be HIUs here, and we've got a 10-degree approach on the left-hand side and a 5-degree approach on the right. Same demands, 30 kilowatts here, and what you can see is at a 10-degree approach, you have a primary flow rate of 750 litres per hour. With a 5-degree approach, that increases from 758 to 1064, but it also is damaging to the return temperature. The 10-degree approach will give you a 26-degree return, whereas the 5-degree approach gives you a 30.8-degree return. Now, the 5-degree for me, it would be the absolute minimum. In theory, you can use whatever approach you want, and I often get asked, are your plate heat exchangers suitable for a 2-degree approach, for instance? And Any exchanger is suitable for any approach, but it has negative ramifications for the performance of the system the more you reduce that approach temperature. So it's something we need to think long and hard about. And for me, I've never normally gone below 5 degrees on typical sizing of a system. When we start to look at the system as a whole, you can see here I've done a calculation, and all I've done is adjust the approach temperature of the heating circuit. And what we can see here, with a 5 degree approach, we have here a 29, well, let's call it 30 degree return temperature with a flow rate of 10.4 litres per second. If we drop that down to 2 degrees, we can see that your return has gone up significantly now to 36. So it's 6 degrees higher in return temperature, and you need another 3 litres per second on top just to apply the same amount of energy. Excuse me. So you can see the benefits of holding a bigger approach temperature. And just to be clear, the approach temperature is the difference between the flow into the plate heat exchanger and the flow out. So just want to talk very briefly about instantaneous hot water production against stored. It was a conversation or a discussion that I think had been settled a few years ago. But as we've started to look at heat pump only networks where the flow temperature has been reduced to maybe 55 degrees, we've started to think, I need to think about storing hot water here because I haven't got enough energy in the primary side to give me instantaneous production, and at least if I store it I can put an element in there, an electrical element, and use that to raise the hot water temperature. But what we need to remember is as soon as you store domestic hot water, you have the potential for Legionella growth, so we need to store it or at least cycle it above 60 degrees C every now and then, and of course that needs a lot of additional energy to do so. Energy that you don't need to do if you're generating instantaneously. And of course, when that cylinder rather is starting to get up to temperature, then your return temperature on your network is going to be significantly higher than it would be with instantaneous. Now, I often also hear the comment, well, if I put a cylinder in, I can maybe use a 12 kilowatt coil, whereas if I go instantaneous, I now need 35 kilowatts. So obviously the energy sensor is going to be a lot bigger for instantaneous than it would be for stored, and obviously the piping as well. Well, that's an error, I'm afraid, because what you find with instantaneous hot water generation, if you think about running a bath, it may take you 5 minutes to fill the bath. The moment you turn that tap off, if it's an instant, the demand stops. With a stored system, you empty that cylinder into the bath. Again, that may take 5 minutes, but then you have to reheat that cylinder, and that takes a significant period of time. And all that basically means is you need to use a smaller diversity factor when you store domestic hot water compared to if you use an instantaneous system. And when you do the calculations, you find that the energy sensor and the pipework are actually very similar, whether you go with one or the other. But of course, as I mentioned, you have to add that additional energy in if you're storing, and you lose your delta T. So it's got quite a few negatives associated with that. And of course, we now have parity in the UK where the HSE, NHBC, CIBSE CP1 are all suggesting 50 degrees C from an instantaneous HIU because it's classed as a low Legionella risk because point of use hot water generation only occurs when you actually want it. So the process of calculating the heat network or doing the calculations, the first thing to do is to work out what your network flow temperature needs to be. And the reason that comes top of the list is it's obviously or normally dependent on your energy sources. So if you're going to do a solely heat pump led network, it may be that you need a flow temperature of 55 degrees, for instance. Obviously, you can use different refrigerants that can give you higher output temperatures, but it may be that your energy source is the dictator of your flow temperature. So once you have that, you'll note I haven't put the return temperature in there at that point, and there's a very good reason for that. We move on. Once we know that flow temperature, we can then do the apartment calculation. So the first thing would be, what are the heating and domestic hot water loads? Are we going to use underfloor heating or radiators? Because that will affect the delta T, of course, and the flow rate required. Can we maximize those approach temperatures? And what domestic hot water output do I actually need? Not a case of going, well, I think it's 30 kilowatts, so I'm going to go 40 and add a bit of extra on. We need to think, what do I actually need in that apartment? Because if you think about every apartment with safety added in and you multiply that back down the network, the result at the energy centre can be significant oversizing. So what do I actually need? And what domestic hot water temperature do I actually need? Again, we talked about that earlier. Once you know what those demands are, you can then select the a HIU to give you that performance. And only once you've selected the HIU do you then know what the delta T is going to be. And the reason for that is quite simple. The delta T from the HIU when it's on domestic hot water demand is dictated by the length of the plate heat exchanger. Mainly, there are some other aspects that affect it, but it's mainly by exchanger length. And the longer the exchanger is, the lower the return temperature is. The shorter the exchanger, the higher the return. So only when you've selected which HIU that you're going to use do you then know what the return temperature will be, and then you have your delta T that you can use to calculate your flow rates. So moving on from that, then you can calculate your network size, the pipework size, the pumps, the thermal store, etc., etc. You can look at the layout of the LTHW pipework, look at that later on. What keep warm strategy am I going to use with the HIUs? Am I going to do it at the HIU or do it on the network itself or a combination? Can we weather compensate this? And this is an interesting aspect here. What we've got to remember now, as we lower the flow temperatures, we're reducing that approach temperature. And we have to be aware of what the flow temperature is all over the network, because if you start to then weather compensate and you end up with a flow temperature that is at or below the set point of the HIUs in the apartments, as soon as it drops below, the HIU control valves will open up to try and achieve a flow temperature that is impossible. And what will happen then is you get maximum flow all over the building and the system will actually crash. So we need to be very careful about that, which is why I mentioned that final point there about ongoing monitoring and adjustment, because it is possible with some of the latest HIUs on the marketplace today that you can communicate with them remotely and adjust their set point temperatures. And it's a really interesting aspect. Something I'm very keen on is holding a stable approach temperature. So rather than have a set point that is fixed on the HIU, you have it relative to the flow temperature coming in. So if you change the flow temperature on the primary side, the HIU automatically adjusts to follow that and keep a stable delta T. So a really smart way of doing things, and somewhere I personally feel we need to get with terminal units, move away a little bit from the sort of dumb terminal unit and have something with a level of intelligence as part of it. So not going to labour this, but you can see on the right hand side there, you've got a single riser in the building and long lateral pipework. And this is where, when you have that long lateral pipework, you have to then keep that flow rate going around that system, that network, and you are increasing the losses. Much better to have, say, two risers, much shorter lateral pipework, and then you don't need to have that constant circulation around the system, and you'll dramatically reduce the losses from the system. I think it's roughly 65 to 75% of all your heat losses on the network come from that lateral pipework. So we need to make sure we optimize that pipework wherever possible. So this is a histogram of a system, which unfortunately is quite typical in the UK. The flow temperature on this project was 80 degrees C, and you can see that the big spike there at the end of the graph, this is measuring return temperature, is around about 78 degrees. So typically a 12 degree delta T, which is really quite poor in today's heat networks, but unfortunately it's quite reminiscent of systems that we've been doing. Hopefully, as I mentioned, with the heat network technical assurance scheme, we can move away from that and move to something more like this. So this is another building, and what you can see now are some distinct peaks in different areas on the graph. So the peak on the far left-hand side is the return temperature that you're seeing from the HIU when it's in domestic hot water demand or mode. So you're getting a real high delta T there, 80 flow, and a roughly 21, 22 degree return. So a very large delta T, great for network efficiency. The peaks in the center are from space heating. So again, you can see here we've got some really well balanced heat emitters, because we've got sort of an 80-48 as an average there, flow and return temperatures. So they've been commissioned really well. We've got good delta T on the heating circuit as well. The small peak on the far right is actually caused by some bypass flow rates, and that this particular system, we went back and recommissioned the bypasses and actually took most of that peak out by just commissioning them properly. But you can see here that we have two distinct delta T's. Now that's important when we come to sizing the system. Rather than pick an arbitrary flow and return, like saying, well, I'm going to have 70 and 40. Hopefully you can see on that graph that if you do that, what all you're doing really is putting a sort of stick in the sand where you think kind of the average return temperature is going to be. Much better to do it more accurately and do it in this way. I have simplified this calculation just to show you the general idea of how it's done. So we can see on the left-hand side the domestic hot water calculation, where I'm using an apartment load of 35 kilowatts, an operating delta T from the HIU of 51 degrees in this instance, and then using DS439 as the diversity standard to do the calculation. So when you do that calculation, you can see 35 by 7 gives you 245 kilowatts of energy required. And then underneath is that flow rate calculation, where you've got your total energy divided by your constant times the delta T, gives you 1.14 litres per second. Moving over to the heating calculation, we can see here I've used 3 kilowatts for the heating load at 20-degree delta T from, say, a radiator system. And I haven't added diversity just for to simplify the calculation here. But as I mentioned earlier, no problem in doing that if you need to. On the calculation side, then it's 3 times 93, because 7 of the apartments are on hot water load in this peak calculation. That gives you 279 kilowatts, and then underneath that is your flow rate calculation. Add those two together and you have now your kilowatt demand and your peak flow rate for the system. So we've used two separate delta T's to calculate the single total demand. So I want to talk very briefly about pump staging, best efficiency pump staging, as we call it. This is an Armstrong technology. What I've hopefully explained is the benefits of maximizing that delta between peak flow and, if you like, low flow conditions. That range of flow rates is best provided from multiple pumps rather than one single big pump, because one single big pump is going to struggle to back itself down to the low enough flow rate that's required for the low demand times. And if that pump's been oversized as well, it's going to be doubly difficult for it to do. So there's mention in CP1 about potentially using jockey pumps. I think for myself, my opinion on that is that jockey pumps had their worth if we've oversized everything, so that we have that ability to get down to really low idle flow rates based on what the peak output of that main pump is. But there are problems in moving from a jockey pump onto the system pump, and a big step change in the flow rate and the head that's being produced. Much better to divide that delta between peak and idle between similar sized pumps, and typically 2 would always be the minimum I would look at, and potentially 3 or 4 on big systems, maybe 6 and 8 pumps to just divide that flow rate up. But what I'm showing here in the graph is pumps have operating points where they're running at their most efficient. And what Armstrong do with our pumps is we test every single pump before it leaves the factory. And when we do that, we're able to map flow and head and shaft rotation speed and power draw into the pump intelligence itself that's built in to every pump. When we do that, we now know at what point that pump is running at its highest efficiency. So what we can see here on this top graph is we're using 3 pumps here, and this is the pump efficiency curve, the red line, and you can see it peaks and then starts to drop off significantly. Now that peak generally tends to be somewhere around the 60% of capacity. Now, if you control these pumps or stage the pumps based on or use the BMS, what tends to happen is you'll run pump number 1 to say 95% of its speed, and then bring in pump number 2, run that up to 95%, and then bring in pump number 3. Well, you can see here, if we're running to 95%, you can see all this time here, this first pump is running at a really poor efficiency point. That's compounded as you bring in more pumps. You get more pumps running at a poorer efficiency rate. The pump itself, our pumps from Armstrong, they have that mapped into that efficiency point, mapped into the intelligence. So what they will do is run to their best efficiency point, and then they'll hold at that point and bring on the second pump and let it come up its efficiency curve, and then hold at that pump's best efficiency point, and then bring the second pump on. And you can see that what the result is, running 2 pumps at their best efficiency point requires less power than running a single pump at a higher speed and a lower efficiency point, much higher pump energy use there. It's called best efficiency staging. It's built into our pumps, and 4 pumps can communicate between each other to make sure they're all running at their best efficiency points. If you have a system that needs more than 4 pumps, we have a controller that can control 8 pumps up to best efficiency staging points. And that controller can also control zones and bypasses on the network as well. And if you need to, it can actually control a jockey pump as well, with all the caveats I mentioned earlier on. So when we look to the plant room, what issues do we see? We see low loss headers. What low loss headers do is they allow circulation back to the energy sources, and so they increase the return temperature going back to the energy sources, so they should be avoided. If you need to have headers, then a flow header and a return header, not connected as 2 separate headers. We see thermal stores connected in a 4-pipe arrangement, and in that arrangement it is just operating as a low loss header again. Thermal stores integrated in such a way where they're not allowed to augment the output of your energy sources, something we'll touch on later, and then overcomplicated valving and hydraulic arrangements around those thermal stores. Multiple layers of thermal stratification or hydraulic stratification, where you're losing efficiency, and of course you're adding in additional pumps each time you have hydraulic separation. A reliance on the control methodology to make things lead, and what tends to happen when you do that, the moment a more powerful energy source comes on stream, it tends to overpower the weaker source. So even if you've made it in the control methodology lead, it can be taken out of the equation once the bigger sources come online. And then, of course, as I mentioned, poor pump control and little pump turn down. Now, this schematic here, I'm going to speed up a little bit. This is sort of a schematic that's shown in the design guide for CP1 that was released a year and a half ago, a couple of years ago. What it basically is showing is your thermal store here in the heart of the energy center, connected by 2 pipes, which are bidirectional. And it's really important to point out here that what is not happening is a circulation of flow down through the store and back to the energy sources. This pipe work here is, as I say, bidirectional, and what we're doing is holding a nice stratified layer between the hot and the cooler water, and because it's stratified, we can measure its location point within that thermal store and also its direction of travel. So we can use that position and the direction of travel of that stratification layer to bring our energy sources on or off to meet what's going on, and we can load our thermal store up, and then we can utilize it as and when we need to. I can probably go and talk a lot in detail about that schematic. It's probably haven't got the time here, so I'll move on, but happy to answer any questions that people may have. So we have at Armstrong have taken that arrangement, we've put it into a prepackaged energy center, which can have, roof, walls, everything is included in the thermal store, the energy sources, all the pumps, and so on. And the idea being here that these are coming off a production line in various different outputs. They are modular, so you can expand them over time as your heat network grows and gets larger and has higher heat demands. But to try and sort of assemble all of the individual components on site just delays that whole process. Much better and speed up our path to net zero by really producing these on a production line approach and then firing them out to the relevant projects as and when they're needed, so they can just be slid in, connected up, and instantly commissioned and up and running. Much faster delivery of your net zero building. So moving on to thermal storage. It's crucial to optimize renewable energy integration. It's crucial to reducing carbon emissions. And on the left-hand side, what we can see in this graph is your typical load profile throughout the day. Big peak in the morning and another peak in the evening. Doesn't really make sense to have an energy source that can provide that peak. Much better to reduce the output of it and actually cover the peak from thermal storage. And similar, when you look at it from a yearly point of view, you can see there's a very large difference between sort of the summer thermal demand compared to the winter thermal demand. So if we can cut some of these peaks off and supply that energy from the thermal store rather from an energy source, then much better. So that's really why we want to integrate thermal storage within the system. Again, we have here another picture taken from CP1 or the design guide, and we can see in this bottom graph here, bar chart, we are taking and giving to the energy, giving to the thermal store as we move throughout the day. So when the peaks hit, you use that energy that you have, that you've stored up in the thermal store overnight, and then as the peak lowers through the day, you then reload that thermal store ready for the peak later on in the evening. So if we look at DS439, there's lots of information in there. DS439 being the Danish standard. There's lots of information on how to size that store, but the important aspect to mention here, this is sort of calculating the typical store size for a typical network. What it doesn't do is look at what your energy sources are, and I would advocate that the sizing methodology is not right and not correct to use that if you have, say, a heat pump only system or a largely heat pump led system. So we need to look at something else. So when we look at those hybrid energy centres where we are integrating heat pumps, then we know the Green Heat Network Fund requires more than 70% excuse me, of annual heat to come from low to zero carbon sources. The Future Home Standard is expected to increase that to around 90 to 95%. But what we've got to remember here is that load profile and run hours of a typical system. What we see is the vast majority of the time, the demand is much, much lower than peak, and it's around about 50% or less for the majority of time. Now, that obviously has implications. So when we say we need 95% of our energy to come from a low to zero carbon source, that therefore doesn't necessarily mean, or doesn't mean, that we need to have heat pumps sized at 95% of peak. Far, far from it. And what we typically see here, and I've pulled some data from various different sources here, that we can look at using a thermal store of around 40% of peak, and that will still, if we integrate thermal storage with the renewable energy source, that will typically give you your 90 to 95% of energy coming from low to zero carbon source. So there isn't a current standard on how to size thermal stores with heat pumps, but there is lots of data out there, and the Ground Source Heat Pump Association make a comment that their minimum size would be 20 litres per kilowatt of heat pump output. I think that is absolute minimum in my view, and I think we need to be looking at a bit higher than that, maybe somewhere around the 50 to 75 litres per kilowatt of heat pump output, 50 being for maybe larger systems where you've got some inertia in that pipework as well, 75 litres per kilowatt on smaller systems where you've got less inertia in that system. So I'm going to just jump to the bottom statement there. Really, for me, thinking, heat networks are all about, delta T and thermal difference rather than kilowatt output. So the way I tend to look at thermal storage, as I look at the operating delta T, what is the operating delta T, and how long do you want the energy to be available from that thermal store? And those two critical factors, I think, are much better for predicting what I'm not predicting, but calculating your thermal store size using those two values. But if we use sort of one of the more simple formula here, you can see that 1,000 kilowatt system, you can size the heat pumps at 40%. That's going to give you, because of this demand profile or runtime profile, around about 90 to 95% of the time the energy is going to come from your low LZC sources. So it'll give you a thermal store size of around 30,000 litres, giving you a total capacity of around 600 kilowatts, and then you can divide the remaining difference up, so that 400 to 600 kilowatts from an additional energy source. So this is if it's a hybrid system. Now that additional energy source could be gas boilers, it could be electric boilers. It doesn't really matter, really. So you can see what that looks like in a graph here. This is the demand curve, if you like, and the heat pump size, it's just 40% of capacity, covers for all this time here, and that's why you're hitting sort of 90-95% of demand. Thermal storage is covering this area, and you can see there's a really small area here where the peaking plant is providing the additional energy. So summing up, I think I've probably talked through most of these as we've gone through, but you can see some of the critical aspects, and really stratification in that thermal store and not allowing flow to go through the thermal store is critical. And we need to think about having a high height to width ratio, so we can see very definite stratification layer, see what it's doing, and you can control from it much more accurately. I hate to see thermal stores when they're tipped on their side, because there may be height restrictions in the plant room. If there are, much better to put the thermal store outside somewhere where it may be on display, but I think it's a good thing. It shows people what's going on where that thermal storage is being used on the network. So they should be horizontal thermal store should be avoided wherever possible. So if we're looking at heat pumps network, what I would definitely recommend is having a 3-port valve arrangement around the energy source. We don't want to compromise the delta T on the network side. So you can see here, I've done a 55 flow with a 17 return here, 38-degree delta T, with obviously an optimized network. And that delta T 38 degrees would not be acceptable to the heat pump. So by having a 3-port valve arrangement around the individual heat pumps, we can now mix the flow into the return and have a microclimate where we're holding a specific delta T just around that heat pump. So it's happy with its 5 degree, and we haven't compromised the delta T on the network side. Of course, the other thing this allows you to do is maybe have a peaking plant that can accept a higher delta T, and then this 3-port arrangement here can be set on that individual leg just for that one particular heat source, which could be CHP or whatever you want it to be, electric boiler, where you maybe can accept, say, a 30-degree delta T. So you've got nice 30-degree delta around that energy source, but 5 around the heat pumps. So a couple of comments I've had about, well, isn't there a conflict between delta T's of the network and the heat pump? Well, the previous slide has hopefully shown how you can address that issue at the heat source itself, at the heat pump itself, without compromising there. But with the latest generation of CO2 heat pumps, we can see that they not only can work on significant delta T's here that you hopefully can achieve on your heat network, but also they do allow higher flow temperatures as well. So they are more suitable for existing buildings, which, if we're going to get to net zero by 2050, we absolutely need to address our existing building stock. Well, here's a way of doing it with maybe a CO2 heat pump. That's not to say you should just ignore that and just connect it straight up to existing buildings without any issue. Obviously, hopefully, as I've explained, every effort should be made to optimize that building, to maximize the delta T within that existing building, move from 3-port to 2-port control, look at the heat emitters and so on and so forth, to optimize that delta T, and then couple it to something like a CO2 heat pump. So if we're looking at heat pump only networks, there are some considerations we need to think about. The capex can be problematic if we're going solely with heat pumps for 100% of the demand, because we have to think also about defrost cycles, and do we need to cover for that somehow? So additional capacity in there to cover for those cycles. So it's quite difficult. And as I explained, if we're looking at a hybrid system, only 40% of the demand coming from heat pumps, and we can hit what we need to hit for our renewable integration. So we need to think about that integration. What does that mean for the associated carbon emissions? If a more carbon intensive source is used for peak, can we move away from that and have some other peaking source which is less carbon intensive? What does it mean for the electrical infrastructure when we're trying to increase infrastructure for electric charging of cars, for instance? And just at that last bullet point, the heat pump only systems, they can be very difficult to get to work, as I mentioned, on existing building stock if a matching refrigerant isn't used. But that's not to say we should avoid putting existing buildings onto networks. And I think on a comment I tend to make quite a lot is that we've got to improve where we've got, and we shouldn't let trying to achieve perfection hinder us from just achieving better. So wherever we can improve a building's performance, we need to do that. It may not be perfect, but if it's a step in the right direction, then it's the right step to take. So I'm going to move on, just very briefly talk about the future, and that is what I would term sector coupling, where we're coupling sectors together, as the name suggests. So commercial, industrial, domestic buildings all connected together on a grid. And that grid will have basically 4 different energy sources. So you'd have electric, you'd have gas, which can be a mixture of hydrogen possibly, and others maybe biogas, but then district heating and district cooling. So they're the 4 energy grids, if you like. And within those grids, you have the sources where you're getting your energy from. Then you have hopefully a storage aspect and a conversion aspect, and then a use aspect. I think I'll move on to the next slide, which probably explains it much better than I'm doing at the moment. So here you can see the coloured bars in the centre are the 4 grids I mentioned, the green being electric, yellow being gas, red being district heating, and blue being district cooling. Here you can see the 4 areas where we have the source of the energy. This is not exhaustive, of course, there's much more than that, it's just an example. This was produced by Ramble, who I've borrowed for this presentation. Then you have the storage aspect here, where we're storing the energy in different forms. Conversion here, where we're converting from one type of energy to another, and then the end users down the bottom. So I'm not going to read through this a lot, but I'll just give you an indication here. One of the objections you tend to get is, well, what happens when the wind doesn't blow? What happens when the sun doesn't shine? Well, this is where this sector coupling comes in, and the storage and conversion aspect. So when wind is plentiful, producing a lot of electricity, we can maybe use some of that additional energy to maybe pump water uphill in a hydroelectric dam, for instance, ready to be released at times of peak requirement, or we send it into the electrical grid, and we then use that here. You can see going into a large scale heat pump, and that energy, electrical energy, could be converted into thermal energy as LTHW straight into the district heating system, or into chilled water into the district cooling system. We can take it into an electric boiler and obviously use that to produce LTHW, again, going into the district heating system. And we can also pull from the district heating system into maybe an absorption heat pump to provide cooling here, and so on. So the point being, you can now get really smart. You can predict when your peak loading is going to be and for what energy type it's going to be, and then utilize the energy. And it's flowing in different directions across this web of energies in various different forms to be able to store ready for peaks, to convert, when you have demand for certain types of energy and so forth. And even when you get to the end user stage here, these end users will be consumers and prosumers. So they're using energy, but they're also sending energy back into the grid. And you can see that here in industry, where we're sending energy into potentially the district heating system. But you can also send the electricity back in from car batteries back into the electrical grid at times when it's not required. So as I mentioned, those end users become not just users but prosumers, where they're giving energy back. There was a report done for the European Parliament in 2018, where they looked at sector coupling and compared it to what's termed a hard electrification approach, which is where any building that has an electrical supply to it, well, we use that electric to provide all the electric heating and point of use electric hot water generation. And what the report found, and there were other studies that backed this up, was that moving to that hard electrification approach actually slowed down the transition to net zero. And in doing so, it also was more costly to take up the hard electrification approach. And looking at Germany, they found that it would cost 600 billion euros more to actually move to that hard electrification approach. And that's fairly obvious, I guess. You know, you have these wet systems already in place in the building, ready to go. Yes, there's some infrastructure required for the district heating and cooling pipe work, but compared to the amount of electrical infrastructure, it's significant. It's in the building as well as in the supply to the building, and all the time when we're trying to increase the electric network for electric cars as well. So it's not surprising really that it delayed that transition. So this is what it looks like on the ground. You can see here we've got various different things. You've got energy from waste here. So an incineration plant providing energy into the district network. You've got, you know, large-scale CHP, large-scale biomass, all putting energy into the district heating grid. You have district cooling on this side here, where we've got some absorption chillers, other chillers as well. Ice storage, there's that storage phase I talked about. And then you have some transition almost technologies, where data centers here, where they're sitting between both the district heating and district cooling grid, where the cooling that they're using, that return temperature, which is now elevated from cooling the servers, can be used or that energy can into the district heating grid to be used by others. And there are transitional technologies as well as data centers. Of course, you can have wastewater, where we're capturing that heat energy and putting that into the district energy network. And that's somewhere that Armstrong also work, where we produce some waste heat transfer stations, where we're capturing that energy, which we'll look at on my next slide. But this was a report done to see what available waste heat there was in industrial processes. And you can see it's terawatts per year. There's a huge amount, or terawatt hours per year, huge amount of energy wasted every year. And it's generally accepted that we waste around 60% of our building demand. So we could take, you know, 60% of our energy demand away if we just utilized that energy that we waste every single day. And we can see from the temperatures here, it's colored on temperature, that even the lowest temperature is still well within the realms of acceptability for a district network. So ideal to use that energy onto district systems. So I just mentioned this earlier on. This is something we have in our range, where we have this transfer station sits between maybe a data center or wastewater system and the district energy network, and it sits between the two and can transfer energy across between those two technologies as required. So I think I've probably come to the end. I have indeed. My contact details are there on that final slide. Apologies for being very top level on a lot of what I've discussed there, but more than happy if anyone wants to contact me at that email address shown. I can go into as much detail as you want on any particular aspect of district energy. So I'll leave it there and hand back over to Josh. Thank you.
Excellent. Well, that was really interesting and useful to hear. Thank you very much for that. I'd like to take the opportunity to thank everybody who's joined us for doing so. It was great to have you with us today. Thank you. But I'd also like to thank Neil and all of the team at Armstrong for sharing with us what they have done today. Everybody's feedback, thoughts, comments are welcome by emailing feedback@cibsewm.org. In the chat, there's a link to details of our future events, which can be found on our Eventbrite page. It'd be great to see you and welcome you to one of those events. CPD certificates should be sent out automatically afterwards, and you can catch up with some of our previous events by subscribing to our YouTube channel. And again, the links in the chat function. Thank you very much, Neil, and the team at Armstrong. And thank you very much for joining us. And I look forward to welcoming you to a future CIBSE West Midlands region event in the near future. Thank you all very much and have a pleasant evening.
Thanks, Josh. Thanks all.